Let's prove this next identity for our exponential function for complex numbers. We are given here that the quotient of e to the power of z sub 1 and e to the power of z sub 2 is actually the e to the power of a difference of the exponent of our numerator and denominator. This is similar to the division law or the quotient rule for exponents for real numbers. But of course, since we're talking about complex numbers now, let's try to show that this is also true by letting e to the power of z be equivalent to e to the power of x plus iy or yi. And since these are still, this exponent still has complex form, or is in complex form, or it has an imaginary unit, let us use the other form, e to the power of x times cosine, you have here y plus I sine y, to show the identity to be true. Okay, so that will be our goal here. So let's try to have our proof here. Okay, so we're going to let first e to the power of z sub 1 be equivalent to e to the power of x sub 1 plus I y sub 1, which would be equivalent to, in this form, e to the power of x sub 1 times cosine y sub 1 plus I sine y sub 1. As for e to the power of z sub 2, this could be written as e to the power of x sub 2 plus I y sub 2, or again, e to the power of x sub 2 times cosine y sub 2 plus I sine y sub 2. Okay? So these are now the two representations we're going to use. Again, we will not be using this because the exponents has imaginary part, and some there might be some complications as to using the exponents automatically in showing this. You can still do that, but allow me to use the second form where the exponent will only be real part, x sub 1 and x sub 2, and we have here a binomial expression which would include the imaginary parts. Now, what we're going to show is this, okay, to show that this one here is true. So you will have, that's not use show, then. Okay, this will be to show, right? So this is then. We have this form, e to the power of z sub 1 over, pardon, let us try to place it here at the bottom. Or let's do it again. Okay. And let's hope that we can actually fit here. E to the power of z sub 1 over e to the power of z sub 2 would be equal to the ratio of these two forms. We have e to the power of x sub 1 times cosine y sub 1 plus I sine y sub 1. Okay? Over e to the power of x sub 2 times cosine y sub 2 plus I sine y sub 2. Okay? Now, take note that this 2 can be taken already as one ratio. This would be equivalent to e to the power of x x sub 1. You have e to the power of x sub 2. Let's stick to that in the meantime. And since x sub 1 and x sub 2 are real parts, so we can automatically use, freely use the division law or the quotient rule. But I'm going to continue doing this one here because I would like to finalize it later on. I sine y sub 1 over cosine y sub 2 plus I sine y sub 2. Okay? Now, I would like to make sure that the denominator here will not include imaginary part. So, allow me to multiply this with its conjugate here. I'm talking about the conjugate of the denominator. So, you have here cosine y sub 2. You have here minus I sine y sub 2. So that I can use difference of two squares later on. Take note that we're multiplying this, and this should be equal to 1, so that we will not be changing the entire expression. So denominator will still be like this, I sine y sub 2. Okay? So for the next part, this here will just be equivalent to e to the power of x sub 1 minus x sub 2. Because, again, x sub 1 and x sub 2 are already real parts, so we can do that. As for the form here, when you multiply the numerator, it will be just something like this. Cosine y sub 1 plus I sine y sub 1 times cosine y sub 2 minus I sine y sub 2. Over, our denominator will be like this. It's a difference of two squares. So the square of this, y sub 2, okay? Or, if you don't want that and you want a step-by-step process, allow me to write it in this manner. Squared and difference of two squares, we have here minus, you have I sine y sub 2 squared as well. Hopefully the spaces here would be enough for the proof. If I can't, I might be adding some pages. So for the numerator, let's use the FOIL method. Okay, so cosine, the first two terms here. So you will have here cosine y sub 1, cosine y sub 2. Inner terms, you have here plus I sine y sub 1, cosine y sub 2. Outer terms, minus, you will have here I, allow me to write first cosine y sub 1 before sine y sub 2. I write this first and this one before this, so that all y sub 1 angles will be written first. And finally, for the last one is minus I squared sine y sub 1 sine y sub 2. That's for the numerator only. This will be divided by the result for denominator. This will be the cosine squared of y sub 2. And take note again, this will become minus I squared. Using the laws of exponents, you will have here sine squared y sub 2. Okay, next part. Still e to the power of x sub 1 minus x sub 2. What will happen now on our numerator? I would like to write this as my second term, but take note we have here the square of negative 1, which is, square of I, which is negative 1. So negative and negative, it will be plus, okay? So I would write the first term as it is, cosine y sub 1, cosine y sub 2. This would be my second term. Take note, again, the square of the square of I is negative 1. So negative 1 and negative, so you have plus sine y sub 1, sine y sub 2. And I'm going to factor out I here. So allow me to use plus I sine y sub 1, cosine y sub 2. I'm taking this out as the combination. So we have here minus cosine y sub 1, sine y sub 2. Okay, that's for the numerator alone. Our denominator would be very unique. You have your cosine squared y sub 2. And again, the result for that is negative 1. And you have a negative here. So you will have actually plus sine squared y sub 2. Okay? Now, allow me to add another page. Before that, let me copy this. This is the concern because I'm using a rational function, or this a quotient. That's why some of the spaces are actually covered already by the first few parts. Okay. So what I need to write here is still e to the power of x minus 1 minus x sub 2. Now, I'm talking about these first two terms. You have the cosine of the first angle, cosine of the second angle, plus sine of the first angle times the sine of the second angle. It follows the concept of the sum and difference formula specifically for cosine. But since it's plus here, the other form for that is actually, you will have here cosine of the difference of y sub 1 and y sub 2. Yes, if it's plus, minus, if it's minus, this is plus. That's for the sum and difference formulas for your cosine. As for your second group, you have plus I. This will also cover, this one here, also cover difference formula for sine. Okay, this is actually equal to sine. Let me remove the parentheses. Sine difference of y sub 1 and y sub 2. Okay, for the denominator, you have something like this. We have the cosine squared of the same angle plus sine squared of the same angle as well. That's actually an identity equivalent to 1. Okay? So what we have here finally is e to the power of x sub 1 minus x sub 2. You have your cosine of angle y sub 1 minus y sub 2 plus I sine y sub 1 minus y sub 2. Now, looking back on our previous form here, take note that if we have something like this, I'm talking about this here. This is the real part, so that's the exponent here. And the imaginary part, or the coefficient, becomes the angle. Okay? Again, the imaginary part, you become its angle, and this one here becomes the exponent of our e. So basically, we're going to return to this manner. This will be the exponent of our e. That's actually the real part. So you will have here e to the power of x sub 1 minus x sub 2 plus I. We have the same angle here. So y sub 1 minus y sub 2. And what is the shorter way of writing this? Now, take note that if we are going to subtract z sub 1 and z sub 2, where z sub 1 has components of x sub 1 plus I y sub 1, and z sub 2 has components of x sub 2 plus I y sub 2. If we're going to subtract this portion here to get that, okay, we're also going to subtract the notations here. So we have x sub 1 minus x sub 2, and you have here plus I y sub 1 minus y sub 2, right? Or I y sub 1 minus I y sub 2, where you can factor out that plus you have I y sub 1 minus y sub 2, similar to this form here. So what does this entire expression be equivalent to? This is actually equivalent to the difference of z sub 1 and z sub 2. So we have here e to the power of z sub 1 minus z sub 2. This shows, okay, this is our goal earlier, that if you're going to have a ratio of two exponential equations or functions with exponents with our complex numbers, you can actually just simply copy the same base and subtract the exponents, just like the division law or the quotient rule for the real numbers, or the exponents for real numbers. Similarly here, we're able to establish that to be true. Okay, so for this and for some instance later on which this will be used, we can actually use now this as we have proven it already. Thank you very much for watching.